It's now time to connect all the concepts that we've learned over the last many weeks, mainly concepts dealing with parabolas and quadratics. Now remember, quadratic just means x squared, and of course x squared is going to be a parabola. So we're going to connect these ideas with application. Actually, we'll be doing this over the next couple days, and the paper that you have in front of you, yeah, it's pretty loaded. There's a lot of information on here. Just so you know, the first half of the paper is to be more like notes and examples. The second half of the paper will become a graded assignment, and finally there's even a small mini project that you guys will complete. And all of these, of course, we expect and know that they'll be well done as we finish our chapter, or we get close to finishing our chapter here again on quadratics. Now, do you remember at the beginning of this unit, we saw that projected objects, that is objects that are like thrown or shot up in the air, of course, are affected by gravity. And so they definitely are going to follow a parabolic, flight path. Let's apply that simple idea now that we have some more knowledge about the parts of a parabola and ways that we can find them and solve them. What we have here is the path or height of a batted baseball, and it's given by this equation. Now, your first instinct might be, geez, I don't know much about that equation. Look, it's got that strange coefficient. It's a decimal. What do I know about that? Well, there's a lot that you know, actually. If you think about it, we can actually start at the last number. That is the y-intercept. And that would kind of make sense based on even where this little diagram is shown, that my graph would start at 3. Now, it is going to be a parabola, right? It's a parabola because it's x squared. And, well, it's a negative. It's got a negative a value, so we know it's going to be a parabola that opens down. Now, it does help to know a little bit about baseball, but basically the ball's going to go up and it's going to come back down. That is a classic example of a projected object. So what can we do now with this illustration of course, a parabola? Well, we can answer some good questions. How about the first good question? What does the y-intercept represent for this situation? Well, we kind of already answered that, right? The y-intercept, which was 3, is going to be the starting. It's going to be the starting height, specifically of this baseball. So the y-intercept represents what we expect it to be, the starting value or the starting height. How about another good question? How about the maximum height? Now, the maximum height should make your eyes go to this spot right here, which we know is the vertex. In fact, I'm going to emphasize that a maximum is always going to be related to the vertex. What do you know about the vertex? Well, you know that there's a way to find it. There's a formula for the vertex. That formula is the opposite of b over 2a. So now we're on a little journey to finding the actual values of this vertex. Now remember, your b value would be the number in front of x. That's just the number 1, so it's really -1. And then it's all over 2a. A happens to be this strange decimal, but hey, it's all right. We can still plug in that decimal. So we get -1 over 2 times -0.0032. Now make sure you can put that into a calculator. If you're putting it into sort of a modern calculator, you would need to use grouping symbols around the entire denominator. I really encourage you to put that in your calculator and not just copy down the answer I'm going to give you, because soon you're going to be expected to get something like that on your own. Again, as long as you use those red parentheses and you put that in your calculator, you should get 156. Now, 156, that may or may not seem big to you, but what I do want you to realize is that 156 is just the x value out to that vertex. So yeah, we're looking for the y value. We're looking for the height. So I have another step. I need to take 156 And that's right, you have to plug it back in. Now, of course, you plug it back into the original equation, and whenever you plug something into an equation, you want to plug it in carefully. This equation's got quite a bit going on. It's got negatives, it's got a square, and it actually has the number x in two places. So I plug 156 back in, and, well, same thing. I really encourage you to put this in your calculator. Honestly, this one you can just kind of type in the way that it's written, but you do want to make sure that you do the squaring first, and then you multiply by the negative 0.0032 second. Again, if you do put it in a modern calculator correctly, you're going to get 81. But don't just copy it down. Don't take my word on it. Make sure that you can get that value. 81, now that would be the height. That would be the y value of your ball. So another good question, answered by using the vertex. How about this third question? How far horizontally will the ball travel? Now, when you think about the horizontal distance of the ball, we'd be talking about the distance out here to this point, the x-intercept. The x-intercept is going to be basically the special point that I'm trying to find on my parabola. Now remember, an x-intercept is always when the equation is equal to 0. That is when you plug in a 0 for x. So I plug a 0 into my equation, and uh-oh, what did I do? Well, I just created a quadratic. Formula. Okay, now the only way to solve this equal to 0 is, again, to plug this crazy thing into the quadratic formula. But it's not terrible. It's just the opposite of b. B, remember, is the number 1, so the opposite of 1 plus or minus the square root of b squared minus 4. Okay, now I got to use this negative decimal here, so minus 4 times a times c. And of course, it's all over 2a, so we want to make sure that we get that also set up correctly. Now, same thing. Don't just take my word on it. You want to actually type this into the calculator, and I highly recommend that you type in that red box individually. I encourage you to type in just that red box so that you can individually get the value of 1 squared minus 4 times negative 0.0032 times 3. Don't just take my word on it. Make sure that you can get that value. So yeah, it comes out to be itself kind of a decimal. Usually we'll just round that decimal place. Or, yeah, do we have to round that one? Yeah, we get 1.0384. Notice that I also went ahead and simplified the denominator to negative 0.0064. Now, next you want to take the square root. You want to take the square root of 10384. So when you take the square root of that, you end up now with 1019. At this point, I'm going to kind of round it to like 3 sig figs, just so it doesn't become a big monster. Now I've got negative 1 plus or minus 1019, and it's all divided by negative 0.0064. Remember, when you get to a situation like this, there's actually 2 answers that you can get. One of the answers that you get is the one that comes from adding. So negative 1 plus 1019. And when you add, you get 019 divided by negative 0.0064. The other situation that you get is the one from subtracting. Now when I do the subtracting, I'm actually going to end up with a negative number. It's going to come out to be negative 2.019 divided by negative 0.0064. And I know I'm kind of running out of space there, but yeah, I'll tell you what, let's just put the second answer over here. Here, we'll just put it right here. So When you do the subtracting, you get negative 2,019 divided by negative 0.064. Okay, now it's an application problem, so we've got some decimals that we're dealing with, but basically this one is a positive divided by a negative. Positive divided by a negative is going to come out negative. And if you divide the numbers carefully, you end up with technically 2.97. That is negative 2.97. Over here, though, I have two negatives, and if I divide two negatives, I end up getting 315. And that is positive 315. Now, as you look over these two answers, one of these is going to best represent that x-intercept. Remember the x-intercept that was up here in this graph. I got to zoom out for sure. And I'm pretty sure that that x-intercept out there is positive. And so the positive 315 is the one that's going to make sense for this problem. We'll zoom back in and we'll make sure we kind of circle that one. So I've got 3 points on this parabola. I've got the starting value, which is the y-intercept. I've got the vertex, which represents a maximum height. And I even have an x-intercept way out there at 315. That was quite a shot. Maybe that was actually a home run. What if a pattern of numbers, what if a pattern where that is a set of points does not look like a perfect parabola? Like, what if it's not just a projected object that, because of gravity, makes it look like a perfect parabola? Well, the question is, can we still create an equation? In other words, can an equation still be used to model the pattern of those points? Well, the answer, thank goodness, is yes. And so if numbers don't look perfect, we can still come up with an equation. And it's just going to require us to use something known as quadratic regression. Now, quadratic regression is the process of finding an equation. So you're still trying to find an equation that would best fit. Remember those words maybe from algebra? A best fit of a pattern or set of points. And again, that's going to be known as doing a regression. Now, this first problem, it's a little bit of a warm-up, honestly. A little bit of a warm-up to understanding this concept known as a regression. It's a matching problem. I got some purple points, and they're not in a perfect parabola. But it looks like I tried to still draw a parabola that sort of matches, or at least best fits, the pattern of those purple points. So which equation is really that blue parabola? Well, if you look at the equations that we have down here, two of them can already be eliminated. Do you see why? Yeah, this parabola is opening down, isn't it? And if a parabola is opening down, I'm pretty sure that the leading coefficient can't be positive. So I can actually cross off letter A and letter B, because both of those would be opening up, which allows us to start to focus on C or D. Now, letter C is opening down with a negative, and letter D is opening down with a negative. They both have an 8x, but there is one difference, and that difference seems to be the y-intercept. Now, one of these suggests that the y-intercept could be all the way down at negative 32. I'd like to consider, though, that if you extend the y-axis a little bit, and you kind of extend your graph a little bit, you should agree that negative 32 would be way too far down. In fact, it probably makes more sense for the y-intercept to be closer to negative 10, to be closer to this y-intercept. So through a little bit of a process of elimination, I'm able to deduce that choice D is going to be my best fit regression equation. Now you could, if you want to, you could always graph that equation, perhaps using Desmos, which is what we're going to get into next. If you flip your paper over, or just open up your pamphlet, what we're going to do is we're going to talk a little bit more about how we can use Desmos to help us with some regressions. Now, you do want to fire up Desmos. If you're on your computer, you're going to want to open up another window. I really encourage you to use kind of like a split screen here or be able to toggle between the two windows. And I'm going to be showing you a process known as regression, where you're actually finding the equation using Desmos. Okay, now we have 3 steps that are shown up here, but instead of going through those 3 steps right now, how about we just mention the 3 steps when we get to them in these problems. So, what we have here is the desire to find a quadratic equation that is going to best fit these points. First thing we're going to need to do is we're going to need to graph the points. Now, anytime you're graphing, you do want to make sure you're graphing correctly. -2, -2 is definitely down in that lower quadrant. How about 0, 2? And finally, 3, -4. Now, as you look at these 3 points, you might say, geez, where's the parabola? It looks more like a triangle. But the truth is that we can always envision, if you will, we can envision a parabola that could best fit these points, just knowing a little bit about, well, about the shape of a parabola and how it could perhaps connect, at least best connect through these points. Now you might say, Ms. Naylor, how did you know for sure to draw the parabola like that? Well, I didn't know for sure, to be honest. I'm actually just kind of making my best guess. But Desmos does know for sure. It's going to be able to help us find this equation, and it's pretty slick. Okay, and that's what we're going to do next. We're going to find this regression equation using the Desmos and the steps that you have on your paper. So go ahead and go to desmos.com /calculator. Make sure that you get to the screen that allows us to actually type in equations. You want to go to desmos.com /calculator or click the graphing calculator option on Desmos. Now, to do a regression, the first thing we're going to need to do, according to step 1, is we're going to have to add an item. So you push the little plus sign in the upper left corner, and we're going to insert a table. You see, a table is the only way that Desmos allows you to type in individual points. And so we've got the points, well, we have the point -2, -2, and we also have the point 0, 2. It's actually a little easier to do this on a computer. I'm trying to do this on an iPad, whoops, and the point 3, -4. Now you can see, I hope, what's happening over here is that Desmos is actually graphing those points. That's pretty cool. See, a table of values is the only way to get a graph of points. Now, if we had to, we could adjust the window using the little wrench in the upper right corner, excuse me. This window seems like it's fine, but I do want you to kind of notice where we have the X parts of the window and then the Y parts. Again, what I have here is fine. If yours happens to be messed up, you can always kind of go back to the old standard -10 to 10 and -10 to 10. But basically, that's allows us to see these 3 points. Now, here's the key step. We're going to do step 2, which is to calculate the regression equation. Now, in order to do this, you're going to use a certain sort of formula, a certain type of code, and that code is printed on your paper. It does say y sub 1. Now, to get the sub 1, you just type y, then 1. Whenever you type y and the number 1, it assumes that you want that to be a sub 1. Now, the main thing here is to find and use the tilde symbol. On your computer keyboard, the tilde is like in the upper left corner of your keyboard. On Desmos, I can click the ABC button, and I can choose the tilde symbol. What is this tilde symbol? Well, it's a way to tell Desmos that we don't want an equation, but rather we want to find an equation. You see, when it sees the tilde symbol, it's going to find an equation based on the notation that you are creating. Now, the notation I'm creating is of a quadratic equation. That is an equation that is of the form ax squared plus bx plus c. You can just use your keyboard to type this. I have to use the Desmos keyboard. Now, I messed something up. I didn't do it on purpose, but I messed something up, and that's why I'm getting this exclamation mark in the left-hand side. You see, I forgot to say x sub 1. The reason I have to say x sub 1 is because Desmos needs to look at the table that I created with x sub 1, as well as the y sub 1. Now, as soon as I type that in correctly, that is, one more time, y sub 1 tilde ax squared sub 1 plus bx sub 1 plus c. As soon as I type that in correctly, Desmos interprets this as a regression. And what it just did is it came up with the equation. Look at the parameters at the bottom of your box. It gave the value of a, it gave the value of b, and it gave the value of c. It actually gave the values of the equation that's going to best fit those points. And if you look over here at your parabola, you should conclude that it's passing perfectly through those points. Well, that was kind of nice. It was able to perfectly create an equation that models the pattern of those points. Now, what you want to do is you want to copy this equation down to some decimal places. So what was the a value again? It was negative 0.8. Of course, that goes with the x squared. What was the b value again? It was 0.4x. And then the c value was plus 2. And that, ladies and gentlemen, is the regression equation for that parabola. Now, what does that mean? That means that that would be the equation that we can use to answer some good questions, like this question, trying to find the highest point. Now, you might say, well, the highest point, I mean, I can kind of see that on my graph right here. Okay, yeah, I mean, I can kind of see it on the graph, but what if we use the equation to find it, to predict it? Again, to get the actual value. Well, that means it's going to be another vertex question. And all I need is the opposite of b over 2a. Now, do you notice that I'm using the a and b values from my actual regression equation? So we end up with negative 0.4 over 2 times negative 0.8. Now, just like we did on the front, don't take my word on it. You need to type this in your calculator. You need to type it in. Make sure that you can get 0.25. Make sure that you can get that, because you're going to be doing that on your own in a few moments. But 0.25 is just the x value, right? We need the y value. And the y value comes from plugging the x value back in. So I'm going to plug 0.25 back into my equation, and I'm going to plug it in for x. Of course, it gets plugged in two places. And, well, I know, don't get tired. I hope you don't get tired of me saying it, but you have to make sure that you can plug that in, that you can do that computation on your calculator. That comes out to 205. Now, what we just discovered is that the highest point is a little bit of a decimal. I don't want to say that it's off, but I do want you to realize that it is a little bit to the side of that red point. Yeah, this red point here, this 0.2 point, is not my highest point. Rather, it's right here at 0.25, comma, 2.05. Let's try a problem that's a little bit more of an application, in other words, that actually is related to something a little bit more in the real world. This is going to be the last problem that we do together, so make sure that you're still with me. What do we have? Apparently we have what's called a jumping water fountain. Now, if it's hard to see this on your paper, there's basically this circular kind of pool, and there actually is another one kind of over here. What's happening is water is being shot up, and it's jumping over here to the next pool. And at Disney World, this creates like a fun little experience, honestly, for people to watch, as the water seems like it's jumping from pool to pool, and then it might jump over here to another pool that could be like in another spot. The idea with these jumping pools, these jumping water fountains really, is that they are affected by gravity. Since they're affected by gravity, they're going to follow a perfect parabola. Do you think we can get an equation for this parabola? I bet we can. We just need some points. We need some points. Now, I'm going to encourage you guys to use the same points that I find. Let's begin with this one right here. That point right there looks like it's going to be at 6:15. Check that, 6:13. Now, to save yourself a little bit of time, you don't really need to count all of these. You honestly can probably just take my word, 7, 8, 9, 10. You can take my word on it that these points are on your parabola. So I feel like I'm ready for this point right here. Actually, you know what? 6:13, yeah, you're right. 6:13 is actually right here. So we'll move that over. But just use these points. You can quickly find them on your paper. That one's at 10:15. This one's going to be at 16:14. Again, hopefully you can find it pretty close to mine. You don't have to be counting all of these to save yourself some time. I'm just going to tell you that we have another point here at 19:12. By the way, if you're saying, how did you get these points? Well, to be honest, I just kind of looked at my graph. And as I look at my graph, I noticed that, well, there's some points on it. Am I trying to find some like perfect points? Yeah, I'm trying to find some perfect points because they're a lot easier to work with than decimals. So could you have other points besides these 5? You sure could. I think you would agree, though, that these 5 are on the parabola, and so they work, and they work for us to do a regression. Okay, now a regression is this process of trying to find an equation, and that means using Desmos. Now, when you use Desmos, you can clear the old stuff. I recommend that you clear it. And then go through the steps again. You want to create a table. This is going to be a little easier for you guys to type in, but you're basically just typing in your 5 x and y values. And of course, these x and y values really make up these points. All right, and the last one is 23:7. Okay, now when you make a table of values, Desmos interprets those as x sub 1 and y sub 1. But how come I'm not seeing them on my graph over here? Well, quite simply because your graph is kind of uses a different window. And did you realize that all the numbers that I found were numbers that were between, give or take, 0 to about 25, and once again 0 to 25. Now, changing the window is just a matter of thinking about the types of numbers that you graphed. So make sure that you consider changing that using the little gear icon, or else you're not going to see your jumping water fountain. Now, in order for Desmos to do a regression, we need to use this tilde sort of notation, this tilde command. And the command is always going to be of the form y sub 1 tilde equals a x, this time I'm not going to forget my sub 1, squared plus b x sub 1 and then plus c. Listen, when you type this quadratic command, it's going to do a regression. It's going to find the a, b, and c values. There they are. Those are the parameters. And yeah, they kind of came out as some decimals and such, but they definitely made the jumping water fountain. That red parabola would be the parabola represented by that stream of water. So you ready to jot it down to a few decimal places? Okay, usually I recommend that you grab, like I said, a couple decimal places. It doesn't hurt to use a few more sig figs, especially when it comes to like that leading coefficient. What's going on here? So we've got negative 0.66. I'm going to kind of still use 2 sig figs, even though that's 3 decimal places. So that's my A value. The B value was the 156 number, 156x, and then 601. Again, what is that equation? Well, that is the equation of this parabola. That's the equation of basically my jumping water fountain. Can I use that equation to answer some good questions? Sure. Here's a question I feel like we've seen a little bit. The longest horizontal distance. The longest horizontal distance. Now, that horizontal distance is going to be referred to, it's referring to this x-intercept. Now, that x-intercept is probably somewhere here, because if you extend the parabola down a little bit, it eventually will come down to that x-axis. But just thinking a little bit into the future, if you extend this side of the parabola down, yeah, it looks like it's going to actually extend outside of the graph, kind of like in a negative place. Maybe I better think carefully about both of these x-intercepts this time, because the distance between these x-intercepts would be my longest horizontal distance. Okay, x-intercepts, fun times. They're always found by setting the equation equal to 0. And when you set the equation equal to 0, yeah, you have created a quadratic situation that requires the quadratic formula. Even though we have decimals here, we can still do the opposite of b, plus or minus the square root of b squared minus 4ac. Yep, we're going to have to deal with these decimals. And don't forget, it's all over 2a. You have to be able to type this into your calculator. You will have to do this in a few moments. I really encourage you to type in all of this stuff, the whole 156 squared minus 4. If you type all that in, you actually get 4.02. And that's what you get when you type it all in. So that means that I'm going to be trying to figure out what is negative 156 plus or minus the square root of 402. By the way, I can multiply the denominator and get negative 132. Now, when you take the square root of 402, when you take that square root, you actually end up with 201. So again, the square root of 402 is 201. But that's going to be part of the plus or minus with, of course, all the other components of the quadratic formula. We're getting close, okay? But we want to be able to find 2 numbers. Remember, there's 2 numbers that come out of this. There's the plus number. Now, when you do the plus number, you're going to end up with 0.405. Or excuse me, just 0.45. So that's negative 156 plus 201, still divided by negative 132. When you do the minus, it's negative 156 minus 201. Yep, that's negative 357. Negative 357. Sorry, negative 3.57 over negative 132. Take 0.45 divided by the negative 132. You get a negative number. You get negative 341. Take the negative 357 divided by negative 132. You actually get a pretty big positive number, 27. Now think about these two numbers that we found here. Do they make sense? Yes, they do. Negative 341. How about 27? Yep, 27. What's the horizontal distance? It's not 27. It's not negative 3. But it's actually the distance between those numbers. Kids, the distance between those numbers would be like 27 plus 3 more. That's going to come out to be 30. And so the distance that I end up with is actually the absolute distance between negative 341 and 27. That's a good question. And it used the x-intercepts. I forgot to write that here at the beginning, but it used the x-intercepts and also used a little bit of adding of those x-intercepts in an absolute sense. Now, this application packet, it has some problems for you to work out. Problem number 1, problem number 2. And when you flip over to the other side, you're going to finish up with an easier problem number 3, and finally a problem number 4 that you're going to try on your own. That's the first part of your assignment. It's 4 graded problems. Okay, you should do a nice job with those. They match very carefully to what I just did with you. When you're done with that, there's another little treat waiting for you. It's a little mini project where you're going to get an opportunity to research a little bit your own parabola. You're going to find your own situation that can be modeled by a quadratic equation. Now, what you're probably going to do is a Google search for something involving a parabola, but I encourage you not to just use the very first search result that you find. Have a little fun. Try to find something that you're interested in. And there's all kinds of things that involve parabolas. Now, in order to do this mini project, you guys are going to also use the Google Doc that's in Schoology, and of course desmos.com/calculator that we were doing. Okay, so 4 graded problems and then a little mini project. Is this a little bit beyond what we normally do in here? It sure is. But I expect you guys to step up and to be able to dive into this, to do a nice job, and to finish up our study on quadratic equations.